We can expand it again in terms of new solution, and let me do that. Okay? This chi, again, let's say, first time I solved this, I didn't find this, but I can find this too. Right? This is again a solution. Maybe not this, but this one. So I can expand it with respect to this solution also. Okay? Let me just do that. Okay? With respect to this solution, I can just do the expansion. Okay? And then same thing will follow, same exact thing. UK star eta, but now there's something different. This set of creation and annihilation operators now should be rewritten in terms of these modes, right? So I have a new set of creation of annihilation with respect to that. So I can just write BK then, okay? And then I can just write this guy too, right? Like this. So now something happened. For the new solution, the Kurtz spacetime, okay, because of the Kurtz spacetime, we have this time dependence issue. Because of that, when we try to fix it, we see that the normalization condition is not enough to uniquely fix the solution. So we have a new solution. With respect to that new solution, we have new creation and annihilation operators. It's like having a different observer, right? Now there are two different observers in that sense. So what will happen? I want to find the vacuum, right? How can I find the vacuum? I have a vacuum, let's say this will hit, okay? Let's say this will, I will say it's A vacuum, vacuum A. And this A vacuum, when it hits, it can be annihilated, or one particle created at a point. But also, there is another observer. This observer sees another vacuum that is defined with respect to these creation and annihilation operators. These are, let's say, B vacuum. It will hit to that too. So now, in the first, we have two different vacuums in that sense. So how can we just distinguish them? We can at least, you know, if we have a coordinate system, if it's through the coordinate system, if there's another coordinate system, there should be some charge transition map, right? Something like that. We can just find a transition map so that we can just move between these two vacuums, these two laddering operators, okay? And we come to that point. Okay, so then we see in these two expansions, we find these different laddering operators, okay? And these laddering operators can be related to each other. The relation is simple, okay? This is the true entity, right? Chi, field chi. So how you expand that chi is depending on the observer that you choose. Okay? So as an entity, chi is equal in two things. So I can just equalize the insides. Okay? I can just say if chi's are equal, then insides should be equal. I can write the equivalents and I can just pick out the Bogle transformations. Okay? That's all. So if I do that, let me just show it to you. So I just take this and take that and make them equal to each other. It's as it is, look like that. Okay, let me show it to you. UK star, okay, BK plus, okay, UK, these are depending on, these guys depending on conformal time. I'm just implicitly writing that, okay. So, alright, okay, UK, okay, nice. B dagger minus K in that sense. They should be equal to, okay. What I write is this, I just pick K to the minus K to write them the same E to the IKX, so that I can just make these guys cancel and say that insides are equivalent, okay? This is this, VK dagger, let me not write that now, AK plus, okay, BK, nice, A minus K dagger, like this, okay? Now, okay, these two are cancelling, I just make the equalization, and in the end, there is something good happening. Okay? I can write the lettering for the A vacuum in terms of the lettering of the B vacuum. Okay? I can write them with respect to each other. That's a good thing. That means that I can transform from one to other. Okay? That's a good thing in that sense. But it has a big implications. Okay? It has a really big implication in that sense. Implication is that means when I try to annihilate A vacuum, okay, I have a lettering up, a creation in B. That means if I try to write it in terms of this guy, the A vacuum, the observer in the A vacuum will see a vacuum, but the B guy will register a particle, okay? Because B creates one, but A annihilates, okay? We will see that now. These are the corresponding transformations between those creation and annihilation operators with respect to these two observers, okay? This is just that. By using this, you can just do that algebraic manipulation, okay? You can just do that algebraic manipulation, and you can write this Bogoliubov coefficients, okay? I forgot to write Bogoliubov transformation. Let me just write that. Okay. Now, these transformations are called Bogoliubov transformations. Okay? And the coefficients are called Bogoliubov coefficients. Okay? So we can also, of course, just take this alpha, this beta and alpha out, and we can write this mode functions in terms of the Bogoliubov coefficients with the other set of observable mode functions. What I mean by this, okay? Let's say UK can be written in that sense. They are just algebra, okay, very easy. You can do it yourselves. Plus beta k, vk, okay? You can also use this, okay? You can start from one mode function and can go to the other mode function by using this Bogoliubov transformation. Okay. So now let us just talk about this Hilbert space of this A and B particles. Okay. Now we know that this A vacuum and B vacuum we can create by using these lettering operators, this creation and annihilation operators. We can create some particles. Okay? If we create with A, we will say A particle. If we create with B, we will say B particle. Okay? That's okay. So, Hilbert space of A and B. Okay? So, both sets of operators. Okay? A, K, plus, or dagger and nothing, plus minus maybe, okay. Right. Okay, A dagger, K, and B dagger, K, okay. Can be used to build orthonormal basis, okay, in the Hilbert space. Okay. So there are, let's say, there are two different vacuum vectors. Okay. In that sense, let's write A vacuum for this guy. Okay. And B vacuum. Okay. So it annihilates as the same. AK, if you hit to A vacuum with AK, it will annihilate, okay? If you hit BK to B vacuum, okay, B vacuum, it will again annihilate. So, for all K, of course, for all K. So, we now can define by using them, right? By using the creation of A and creation of B, we can now define this A and B particles in that sense, okay? In the excited states. Okay, in the excited states. Two sets of excited states we have, okay? For the A, we have MK1, go, right? And K2, let's say, okay? It will equal to, let me just write it in all setting, it will be easier in that sense. A, K, dagger, M times, A, K2, K1, K2, dagger, N times, and it should act on A vacuum, okay? And B vacuum will follow. Same thing with B, okay? I'm not going to write it. Same thing with B. And then we have the B vacuum. But now, then from that, we can construct also an arbitrary quantum state by just making the linear combinations of those, right? So the arbitrary quantum state can be written like this then. Of course, in the exact state, right? Or arbitrary exact state. So, okay. And arbitrary Q state, let's say that arbitrary state noted as this psi, can be written as linear combinations of those excited states, right? Linear combinations of excited states. Like this, right? You can sum in M and N, right? And then this C, M, N coefficient, this coefficient square will give the property, right? Okay. So, A, and just the combination as I said. Okay? It will go like this. And of course, we just expand it with respect to the basis, right? This is, let's say, this is A basis, this is the B basis. We just expand it with respect to expansion, the coefficients will be changed, of course, with respect to that, okay? I can just pick an M and N, C, M and N, okay? And now B. I can just write it for the B excited state. That is it, simple as that. Okay? Now, there is something interesting happening, right? Because now I have this probability of finding B and A particles. And with respect to what? If I just take the square of this A and B, let me just write A and B. It's kind of confusing. This is the probability to find A particle. This is the probability of finding B particle. Okay? Like this, squares of this. Okay? So, now, there is something interesting happening. Okay? So, B states are in general different than, of course, the A states. But if beta, the beta that I defined in the Bogoliubov transformations, are different than 0, okay, B vacuum can contain A particles. Okay? If beta is different than 0, let me prove it to you. Okay, let me prove it to you. It's really simple calculation, by the way. Let me just show it to you. Simply. Two-line calculation, so that we can show one vacuum contains other vacuum's particles. Okay, and it's vice versa. You can write them in terms of squeezed states. Squeezed states are the exponentials of the Lagrange operators, and you can just find squeezed states from them. But we just now using this. Okay, so the B vacuum, this is our plane, vacuum plane, B vacuum contains A particles. Okay? So, how can we verify that? We can just use number operator, right? Number operator for A observer, and we can just write it in terms of B observer. Then we can just look at the expectation, and we find the number, okay? It's simple as that. So, let's start. Let me just first define the number operator for every K. For the A observer, let's use the observer name, okay? A dagger K, A K is number operator, if you remember. It was in the Hamiltonian, right? Number operator. So, B, okay, 0, N, okay, K, A, right? And then again B. So what I'm trying looking is, I'm just having B vacuum. I try to look at the B vacuum expectation of number operator of A. Okay? You can just think like that. So I just try to look at it. Okay? So how many A particles expected to be inside B vacuum? Okay? So this is that. Just write it. Okay? Let me just write it like this, maybe in the long setting, doesn't matter. Okay, like this, right? Now we already defined how AK is written in terms of B's, right? I can just replace it. Okay. Alpha K, BK dagger, right? Plus beta K, okay, BK, okay, and then alpha K. Why? Because there are between daggers between them, so the coefficient will get a complex conjugate. Okay, BK plus beta K, okay, and B dagger with the minus K. Nice. There's also a minus K in here. Do not forget that. If I forget, please remind me. And 0. Right. So just multiply these guys, and the cross terms, and then hit to the vacuum. Okay. In the end, only surviving term for this is this. Okay. B and B, okay, and then 0, B is there, alright. And then, if you do the calculation, it's basic, it creates an LAX, and then there's B squared, right? It's just this beta K squared with this canonical delta at 0, delta at 0, okay? That's it. So, this is, of course, this is a divergent factor, I know it, but this accounts for this infinite volume, okay? Infinite volume in the spatial distance, it accounts for that. And this mean density for the number of the B particles in A particles in mode K is this, okay? Then we can just write it as the number of A particles inside B, okay? Then number K is not this. Okay? It's this just. So the total mean density is N, okay? It's just taking the integral, of course. The volume integral, okay? Okay, so as I said in the break, this to be finite as a finite number of particles inside. This should decay faster than Q minus 3, okay? This should decay faster than, so that this has a finite value in the integral, okay? So, this means the B vacuum, with respect to A, registers some particles in the density, okay? We have non-zero number of M, and is non-zero if B is zero, B is not zero. That's really important. So, for one observer, something is vacuum, nothing in there, okay? But for another observer, it's not a vacuum. There are some particles in there, okay? It's also, as you give in the example, it's again happens in the Unruh effect, okay? It's the same thing, at least in the logic, it's the same thing. In the Unruh effect, the accelerating detector in the Minkowski space sees particles coming to him or her in the Minkowski flat space in the vacuum state, okay? It's similar. We are using the same kind of transformations, but one of them is in the Minkowski flat space, something is accelerating. This is in the Kurtz space, okay? But the results are similar. So, now, let me just go with this other thing, okay? We now have some problems, okay? We have now some problems. Firstly, we see that vacuum now is ambiguous. It depends on observer, okay? So, but it wasn't the case for the flat spacetime, right? So also, there is some time evolution, and with respect to time evolution, energy is changing. So by heating with the Hamiltonian to the vacuum state, in the later times, maybe the vacuum state is not the vacuum state. So vacuum state might evolve because it can register non-zero number of particles, okay? You can think like this. So what we can now talk about is only, okay, let me just erase here, is only for the instantaneous lowest energy state, okay? Only that, nothing more, nothing less. We can just talk about that only, okay? In the curved spacetime, this is some outcome of studying in curved spacetime, okay? Now we cannot talk about a eigenstate of the Hamiltonian that is the lowest eigen, that has the lowest eigenvalue for all times. We cannot say it now. Because now, as you see from the harmonic oscillator equation, the frequency is time dependent. Now, as your friend said, the metric is time dependent. Mass is time dependent. Everything is time dependent, and time evolution, the finding the lowest energy state is now can be done only with respect to the instantaneous lowest energy state. Okay, we can just look at it at a time, and we will do that. Okay, so in flat case, what I mean by flat case, the flat space-time case. Okay, vacuum was defined as an, as I said, eigenstate of Hamiltonian with the, this is important, lowest possible energy. So, but this allowed us unambiguously define this preferable set of mode functions, and with that we unambiguously define the vacuum. But in here we don't have this preferred set. Even thinking that in the curved background, this coordinate chains are all coordinate chains are allowed, right? In special relativity it's not, but for general relativity, all coordinate chains are allowed. Okay, the symmetry group is different. With that, now we have to take care about this, okay? Since all coordinate chains are allowed, we don't have a preferred observer, and with that, we now don't have a preferred vacuum. Vacuum is ambiguous, okay? So, now, we now cannot find it, but at a moment of time, okay, at a zero, okay, at the moment of at a zero, we can define instantaneous vacuum, okay, and we will call it as, let's say, at a zero vacuum, okay, like that, as the lowest energy state. So now, we had that Hamiltonian, but now we have to rewrite the Hamiltonian, okay, in terms of the mode functions that we have. But now we have this time dependence, and the form of the Hamiltonian will change according to that, okay? So if I just write it, if you remember, H was, I'm just passively writing it. You can do the calculation, it's the same, but now you will take more derivatives than before, okay? It's only that. You will take 2 or 4 or 5 more time derivatives and you will find the result. It's really easy calculation, you can do it, okay? I believe that you can do it. If you cannot, you can tell me, I will just show the calculations to you, okay? Okay, this was the Hamiltonian, and you remember chi, right? Chi was 1/square root of 2. Now the form was adjusted according to this time dependence. Okay, time dependence. IKX, VK this guy, and AK plus, right? I minus IKX, right? VK, right? And AK dagger. If you take this time derivative, then you can just replace it inside. And in the end, you will find the Hamiltonian of this form, okay? You will find the Hamiltonian of this form. 1/4, it will be seemingly significantly different than the flat space Hamiltonian, okay? Okay. AK minus AK minus F is a new function, it's minus sign, plus AK, let me not write minus and plus, but I can just write this, let me write with daggers, it's easier. Okay, FK plus, now the familiar part comes. The familiar part from the flat spacetime comes, okay? So, okay. If you do all the calculations, it's really easy. You can just think of it like this. You have this guy. You will have 2 times time derivative. Now time derivative will act on this guy. This will have time derivatives. And then you will just replace it inside. You can gather them. So the choice of gathering in here, the choice of gathering is really clever. Okay? Because when you try to look at the 0 point energy, you will just take this AK, EK. Okay, AK, EK. And then, if you try to look at, do I have an instantaneous vacuum for all times? You have to look at this function f. So, let me just show what the functions are. Fk is actually a differential equation. If you set it to 0, then we will. You can see the first order derivative with square, okay? With square set. And then Ek, okay, Ek is this. Okay, this. So now, with respect to mode functions and with respect to this Lagrange, we have this form, okay? So, what can we do now? We can just look at the expectation value of the Hamiltonian, okay? We can just check the expectation value of the Hamiltonian. We can just check whether if this is the lowest energy state by looking at that expectation value. We can just check it. Or we can do something else. We can just check that whether this is 0 at all times. If this is 0 at all times, then we will see that the lowest energy state is possible, and this is that. And we will see, okay, we will see. So let me just tell you something. If you just pick Ek as 2 omega k, and if you set Fk to 0, it will reduce to something like the flat spacetime, but it is also said that instantaneous Hamiltonian diagonalization is diagonalizing the Hamiltonian in that sense, okay? Is diagonalizing. So, in that sense, you can now, with this choice, you can now act to vacuum. By acting to vacuum, you can of course find vacuum of instantaneous Hamiltonian diagonalization from the diagonalized Hamiltonian. And you can find the other states by using the Bogoliubov transformations again. That's again a choice, okay? So without any problems. So let me now just try to show you that a vacuum state could remain as the eigenstate of Hamiltonian if and only if this F is 0, okay? Let's check that. Let's write Fk, okay, is what? Vk, okay, Vk prime square plus omega square, this is of course dependent on eta, Vk square is equal to 0, okay? We can just look at it. So this differential equation has exact solutions. The exact solution is Vk is equal to C times exponential, okay, plus or minus integral Vk eta, okay, is familiar. If this was time independent, this will give you eta, and the solution was the same as the harmonic oscillator one. But since this is now time independent, you will see that all the calculations, the harmonic oscillator equation should be satisfied. But with the time dependent case, harmonic oscillator equation is not satisfied. This contradiction, okay, gives some problems, okay? Let me just write. So if you try to solve this with this, if this is depending on time, the conformal time, okay, the harmonic oscillator equation is not satisfied. Okay? So the operators Ak at eta 0 and Ak at eta 1, okay, defining the instantaneous vacuum states eta 0, 0 and eta 1, 0, okay, it's just at eta 0, vacuum state at eta 0, vacuum state at eta 1, okay, at two different moments of time are related by Bogoliubov transformations. Okay. And the expectation value of the vacuum state, we already write it, no? The expectation of the vacuum state at a time 0 with the Hamiltonian at a time 1, okay? Oh, it's time. Will be, okay, equal to this guy. Okay. This integral k, you know, this omega with eta 1, k, right? And then this guy, ak there, eta 1, ak eta 1, right? plus 1/2 is Dirac delta term that will hit on the vacuum at eta 0. Okay? So Hamiltonian should evolve the vacuum in that sense. Okay? So what we will find, again, we have this infinite spatial distance term with this d cubed k. There is no over now. Omega k at eta 1 with 1/2 plus we already found from the number operator. For the number operator we found it, bk squared. Okay? So bk is the corresponding Bogoliubov coefficient for this guy, for the time evolution. Okay? So let me just write it then. Unless bk is 0 for all k. Okay? This energy is larger than minimum possible value. Right? Hence, the after time passing, okay, at eta 0 time vacuum, when it comes to eta 1, it contains particles, okay? Because if this register particles, as I said, okay? So hence, the state eta 0, okay, contains particles at later time. So, what can you do then? You always find these particles at later times. Okay. Let me just show it to you. You can just look at the minimal fluctuations. Okay. You just try to optimize by using the Heisenberg principle. Okay. You can just try to optimize the by using the minimal fluctuations. So let me just state that too. So let me just write minimal fluctuations. Okay. So the value of mode function v k at eta 0, okay, can be chosen to be arbitrarily small, of course. But because of the Heisenberg principle, the derivative of it now will be large, right? Because of the sun, very large, let's say. Let me just write that, very large, okay? So, what can you do? In the lowest energy state, okay? In the lowest energy state, both Vk at eta 0 and Vk prime at eta 0 are optimized. So, generation of large fluctuations are avoided, right? In the sense that the vacuum is basically the state with minimal fluctuations. So, there is no unique best way to describe vacuum, okay? So there is a really easy way to understand why it happens, okay? There is a really easy way, there is a really basically understandable way why this happens, okay? So, okay, So usual, okay, the usual definitions of vacuum are n particle states in Minkowski spacetime. In Minkowski spacetime are based on, as you know, the composition of e to the right I k x minus omega t, or reverse. Okay, so a localized particle with momentum k have a spread delta k, right? Have a spread of delta k. So the particle momentum is well defined if the spread is lower than the momentum itself. If the spread is large, then you don't know the momentum, right? It's the basic thing. So the spatial size, okay, let's say lambda, spatial size, inversely proportional to that spread from the same place, right? So it's something like this. This is inversely proportional to that spread, okay? And therefore, it's inversely proportional. It's much bigger than, in that sense, is k. However, okay, if the geometry of curved spacetime really varies in different regions, okay, then this plane wave approximation is not a well-defined approximation now. And if it's not a well-defined approximation, then you cannot define this k, and you cannot define the particle's momentum, okay? So definition of momentum fails. And it happens even in this conformal flat Friedmann universe. Some of the modes of k are not well defined. So let's see. And you know it, it's really easy basically. So if you write the equation for the harmonic oscillator, and if you say the omega k is negative for negative energy states, for negative energy, right? It's now not harmonic oscillator equation. The harmonic oscillator construction collapses for some frequencies, some modes, okay? So let's say if this omega k is smaller than 0, okay? Of course, mode expansion will still make sense. You can just expand it in terms of, I don't know, another function like hyperbolic function or something. But in the end, okay, the interpretation of the corresponding states in Hilbert space in terms of physical particles are problematic. Okay? So even in the curved spacetime, as we said before, right, there is no preferred coordinate system. It is again a problem because in that sense you can just change the coordinate system. For every coordinate system you have a new thing, and there are some problems, of course. And in the presence of gravity, right, negative energy we have sometimes in the ground states, and true vacuum states is again problematic. So we need to understand one thing, okay? We need to, if we try to work on curved spacetime setting, we have to release the notions of this vacuum and the particles. We have to just redefine them, but we are really good with it. The reason is, we see that even with this, the particle detectors are good to go. if you try to probe it with experiment, they are good to go. Because the reason is, when we try to do an observer, when we do observing something, when we do the experiment, we will just observing the expectation value of the total energy momentum, okay? We, of course, because of the quantum effects, we have some vacuum polarization effects, okay? We have some vacuum polarization effects, but in the end, we are just looking at the all over total energy momentum, and all over total energy momentum, even if they register some particles, we can just see it from the accelerator, so no problem, okay? So this, of course, we need to release something, like the existence of vacuum, we have to do some change in that. We need to consider that the frequency now, depending on time, universally expanding, this expansion might create particles somewhere for some observer, but in the end, we can do the detection, okay? Of course, if we can, with the current technology right now, okay? So they are theoretically, maybe theoretically it looks ambiguous in the sense that vacuum is ambiguous, but for the other purposes, even with the vacuum polarization corrections, we can find it without any problem from the total energy momentum transfer. Okay. So, of course, so yeah, in the sense that, of course, yeah, we can always ask, okay, ask these physical questions, no problem.